Okay.
So can I solve this problem?
No, you can't, but this one has to. Inside. So when you have thermal production, you can't capture that within resistance. This one you have to solve with heat condition code. Thank you.
Well, there's a problem.
Edwin, right? Yeah, I got your email. I just haven't had a chance to respond.
So, because what I'm confused about is asking about with the contact lens.
Mhm.
So when I did my problem, I put it at the end. So why would we put it not at the end and still keep convection outside?
So convection is always going to be the outermost layer here because that's where the air is. And so if you look at the path that the heat has to travel, it has to cross convection of the inner layer, then the eyeball, and then the contact lens, and then convection here is on the outer lens. Although if as long as the values that you put here are the same and you're just computing the whole thing, it doesn't really matter what order you put in. But if you were computing the surface temperature, it would have to be right.
Okay.
Yeah. So the order matters for the surface temperature, but for overall Q, it doesn't matter.
Okay.
Yeah.
Okay. Thank you.
But yeah, I'll double check the values. Yeah, afterwards.
I just want to, so what's the difference between this
Mhm.
and this?
This one should not be,
Not to be used
yeah, because the LN, you should, natural log, you should only use that for cylindrical system.
cylindrical?
Yeah.
Okay,
So for spherical system, you should always use the one over.
and that's conduction, right?
Exactly,
For spherical, right?
exactly,
Okay,
yeah.
so that's a difference. Okay, because that's what I was wondering, but I couldn't remember. I couldn't remember if that was how we got that basically.
Oh, yeah, yeah. So that one we used it. The reason for that is because spherical systems, we have a different equation there.
Mhm.
And so we end up with a different expression for this.
Okay, that makes sense. Okay, thank you.
Mhm. How's it going?
How we living today?
Oh, good.
Good.
How are you? Good.
Well. So midterms canceled Thursday?
Unfortunately not, no. already put in all the effort to write it. You guys should take it.
Say it again?
I already put in all the effort to write it. You guys should take it.
Midterm for the big factors.
Mhm.
So we'll be getting what they could provide.
I'll provide it. Yeah. So if you need them, I'll provide them. So you don't have to put that on your cheat sheet.
Okay.
Yeah. All right, it's 1 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. All right, so the day before the midterm, so thank you guys for coming out. I know it's I know you guys are probably really busy with studying, so okay. So speaking of our midterm, so I did post a few things yesterday to help you guys with your studying. The homework-based solutions are posted, so you should see that on Canvas. The other thing that was posted, and someone actually reminded me yesterday, so thank you. I did post a practice exam for you guys as well. So that practice exam, that's the midterm exam that I gave 3 years ago, which is actually the last time I taught this class. And so you can expect, obviously it's not going to be the same exam as the practice exam, but it's going to be very similar. So I would definitely check those out. Unfortunately, I don't have the solutions for the practice exam. They were written on a piece of paper that was lost sometime 3 years ago. So I don't have the solutions for that, but at least it should give you a feel for the questions. It'll give you some more practice as well. And if you do solve the questions on the practice exam, you can definitely email them to me or come to office hours. And I'd be very happy to go over with you as well. But I don't have the solutions kind of written up and formatted pretty nicely. But homework solutions should be there. Okay. Other thing I want to mention, just because a few people have asked me this, for the 2D conduction type problems with the shape factors, if you guys need a shape factor, I will provide that for you. So there's no need for you guys to copy that big table into your cheat sheet. There's a lot better for you to have on your cheat sheet. So if you need a shape factor, I'll give it to you. Don't worry about putting that whole huge table there. The only thing you should worry about is how to use the shape factors, more so than memorizing that whole table. Okay. All right. So today, we're going to continue on with our discussion of convection. So again, nothing that we cover today is going to be on the midterm, but you are going to need it, moving forward. But today, don't tune today out, but maybe you can take today a little bit easy, and just kind of focus your energy towards the midterm exam. Okay. Any questions I can answer before we get started for today? Okay. All right, so let's go ahead and continue. Okay, so the topic that we were covering was, I call it the introduction to convection. And it's kind of the first lecture that we're going to be having on this kind of very broad topic on convection. So, if you kind of break the class down into the 3 different types of heat transfer: conduction, which we just finished, so we're all done with conduction, convection, and radiation. We're probably going to spend the most time on convection because there's just that much to talk about for convection. So today's kind of the first introduction, and over the course of the next few weeks, we'll be going over different situations, different applications for a convection. Okay. So let's define it first. So convection, as we've discussed, many times before, convection is simply just the heat transfer to a moving fluid. And generally, the idea with convection is that when you compare it to just regular conduction, so kind of still conduction, convection almost always is going to enhance the amount of heat transfer that occurs. So, that's kind of point number one, where, whenever you're talking about convection, you're talking about, an enhanced amount of heat transfer, okay? And last time, or last Thursday when we met up, we started talking about why this is the case, right? So essentially, the reason you have enhanced heat transfer in convection is that convection kind of combines two different phenomenon into one thing. So what we perceive as convection is nothing more than just conduction of from a surface to a fluid. Right? Conduction heat transfer, remember, the way we define that is, molecule to molecule transport. So, neighboring molecules just naturally just kind of transfer energy and transfer heat to each other, right? So that's going on. But convection also combines that together with a bulk motion of the fluid moving past the surface. Okay. So, I kind of made the joke last time that, some people think that there's really no such thing as convection. Convection is essentially just the same as conduction, except you're just moving the fluid particles along so that, whenever a fluid particle heats up, it's just swept along with the flow and it's replaced with kind of fresh, cool particles, so that, you kind of get this enhanced effect. Okay. So that's kind of the main thing with convection there, right? And right at the end of class on Thursday, we came up with this expression to talk about kind of the effects or how we determine the convection coefficient. So the convection coefficient is something that we've been using. So we've been using this for almost the entire semester so far, and so that is our convection coefficient H. Okay. And the convection coefficient is a very interesting tool. It's a very interesting phenomenon because essentially what the convection coefficient does is that it summarizes or it kind of, pulls together or aggregates the net effect of convection for that fluid. Okay. So typically, whenever we do calculations involving convection, we use this convection coefficient just because it's a lot more convenient. Because what you'll see, over the course of the next few weeks, that if you were actually going to solve everything that's involved with convection, it's a lot more difficult. It's usually a lot more convenient to have this simple coefficient here. Okay. And so we know how to use this coefficient. We've been using it for a while. We use it in Newton's law of cooling. So I'm not going to write that again. But the last expression that we came up with on Thursday was we said that H, or the value of H, is equal to minus KF partial T partial Y divided by T minus T infinity. So this right here, this is not a formula that we're actually going to use to compute H. The only reason we brought this up and the only reason we derived it was so that we can kind of start a discussion to talk about, what are the factors, or how do we even, what are the factors that even go into computing H? Okay, and in particular, there were two things in this expression that I wanted to highlight. So first thing was KF, right? So KF right here, this is the thermal conductivity of the fluid. Okay. And so what this tells us is that the value of H actually does depend on which fluid that you're using. And so what this tells us that, if we compare the thermal conductivity for a relatively low, if we compare the convection coefficient for a relatively, insulating fluid like air compared to something like water, water is more likely to have a higher value of the convection coefficient just because water is a much better conductor of heat. Okay. And then, there's fluids all along that spectrum too. So, probably the most conducting fluid that's out there right now, or one of the most, is liquid mercury. So liquid mercury is very well conducting because its thermal conductivity is so high. Okay. So, the type of fluid matters, which, probably is fairly intuitive. The other thing that matters here is this expression here, partial T, partial Y, which we said last time, this was a property of the boundary layer. Right? So how that gradient forms is going to influence our value for H as well. And so essentially what this is telling us is that H not only depends on the type of fluid that we are using, but it also depends on the properties of the flow field as well. Okay. Which of course, the only way that we can really compute this is through fluid mechanics. Okay. So convection, convection is a very complicated phenomenon because you not only do you have to know everything that has to do with the thermal side of it, so the energy transfer, energy balance, things like that, but you also need to have a deep understanding of the fluid mechanics as well. And I don't think I need to tell anyone in this class how difficult fluid mechanics is. So yeah, so this is going to be the topic we spend the most time on in this class because it's probably the most complicated. It has the most things to do with it. Okay. With that said, we're not going to be actually solving for fluid flow fields here. So, we're not going to see Navier-Stokes, but it is good to have some intuition in fluid mechanics. Okay. Okay. Any questions on this so far? Okay, good. All right. One thing I do want to highlight here, before we start talking about, the fluid mechanics is, there are different kinds of convection coefficients. So the two types of convection coefficients that you can have are local and averaged convection coefficients. Okay. All right. So let me give you an example here to kind of show you what that means. Okay. So let's say that we have a fluid flow that's going around some arbitrarily shaped object. And so, we'll say we have flow around a potato. Okay. So we have an arbitrarily shaped blob here. And we have fluid that is kind of flowing at it from the left. Okay. So this potato here, it's going to impede the flow. And so the flow just cannot just, clip right through the potato. It has to actually go around it. And so you actually, look at the flow field, there's some really interesting kind of phenomenon here. And so first thing you should notice is that the flow that strikes right at the kind of the middle of the potato, what that's going to form here is that's going to form what we call a stagnation point. Right? The stagnation point is nothing more than just a point in the fluid, a point in the flow that has basically zero velocity in all directions. Okay. It's where the flow kind of stagnates. And usually you get a stagnation point in situations like this when you have a fluid flow that's kind of impinging or kind of striking a surface at a given point. Okay. So from the stagnation point, the fluid has to go around the potato. Okay. Right. So all along the surface here, along the potato, you have a boundary layer that's going to form. Okay. Not only is the boundary layer going to form, but it's also going to develop along that direction as well. Okay. And since this is a fairly blunt object, probably what's likely going to happen, unless you have a very, very slow flow, is that eventually the flow is probably going to separate at some point. So we have kind of two separation points here. This is what usually happens when you have a fairly blunt object in a flow like this. And so you're gonna have flow separation, and back here, you're gonna have very kind of slow flow. And so we call this region the wake region. Right? So in the wake region, usually you have kind of slow moving flow. There's probably, a dip in the pressure back there. And it's something like that. Right. So for a very simple object like this, like a potato, we actually have a very complex fluid mechanics that goes around that. But again, probably don't need to tell you guys, you guys probably had a lot of that in last semester. So this is kind of the situation that we have. Okay. So I bring all this up, not to kind of not to kind of flood you with fluid mechanics knowledge again, but just to tell you that, in the different regions around this potato, right? And so just in this very quick example here, we've identified 4 different regions, 1, 2, 3, 4. Okay. The fluid mechanics in all of these regions here are all looking very different. Right. So whether you're at a stagnation point, whether you're in a boundary layer, where in the boundary layer you're going to be, whether you're going to be at the front of the boundary layer or near the tail end, when you have flow separation and wake region, the fluid mechanics all look very, very different in these areas. Okay, and so it stands to reason, based on kind of what we've been discussing, that the convection coefficients in these 4 areas are all going to be very different as well. Okay? Because the convection coefficient, as we've kind of discussed, relies strongly on the fluid mechanics or the flow patterns in that particular area. Okay. So if we think about the convection coefficients at each of these areas of the flow, we call these the local convection coefficients, because these are the coefficients that are local to each of these specific regions of the flow. So, when either the textbook or the notes or when we refer to local convection coefficients, what we mean is the convection coefficients for that specific region. Okay. Okay. But usually, when we use the convection coefficient in calculations, we don't use the local convection coefficient because they can change, right? So the one that we actually typically use in calculations is known as the average convection coefficient. So this is often used since it's used to represent kind of the bulk convection from the entire object. So that means all the convection coefficients we've been using up until this point, everything that we've been doing in homework 1, homework 2, homework 3, they've all been average convection coefficients because they've been averaged across the entire body, the entire surface. Especially when you have kind of complex geometry, that's what's we've been using. So over the next few weeks, we'll be going over different expressions for different convection coefficients, but you just have to be aware which ones are local and which ones are average. And so, just so that which one to actually use in calculations. Okay. Okay. Any questions on this? Okay, good. Okay, let's talk about well, so far, everything that we've been talking about today has been focused around this convection coefficient, right? And so, if we can find this convection coefficient, or if we can solve for it, then, we can, basically use that convection coefficient in all of our calculations, okay? So this is kind of, what's called the central problem for convection heat transfer. Okay. The central problem for convection heat transfer is very simple. The central problem is just compute H. Okay. That's it. We're going to be spending, 5-6 weeks just, talking about how to compute H. Because it's difficult, and hopefully one sense that I've given you over the last couple of lectures is that convection is really complicated. There's a lot of factors that go into it. And so, even just saying something simple as, how do we compute H, it's going to be very different in a lot of situations. So, that's kind of what we're going to be focusing. So, because generally the idea is that if you can compute H, then there are a lot of methods that exist out there for computing everything else you need to know about the system from a thermal perspective. Heat equation, thermal circuits, lump capacitance method, all the techniques that we've learned so far if you have H, you can plug that into all of those different methods, okay? The difficulty, of course, is finding H. So what you're going to see, you know, especially in your next homework assignment, homework 4, I know everyone's thinking about the midterm right now, but homework 4, you're going to see that the problems that I've given you are actually, they actually look very similar to the problems I've given you up until this point. The only difference is that, you know, you're not going to be given the convection coefficient H. And so, you know, those problems, for those problems, you'll see that, you know, there's going to be a first part of the problem where you compute H, and then the second part of the problem where you actually use it in the calculation. Okay. Any questions on this so far? Okay. All right. So let's start to introduce some of the methods that we're going to use to compute H, because, you know, I know we had that formula from above here, but, you know, again, we don't actually use this formula here to compute H. There are better, more easy ways to do that. Okay. And to start that discussion, we have to kind of do a little bit more review from fluid mechanics, talking about laminar and turbulent flow. Okay. So this is going to be one of the most important factors that leads into computing our convection coefficient. Okay. Okay. Let's define these first. So laminar flow. So the way we kind of define laminar flow, we kind of define laminar flow as flow that's very well orderly, very well, you know, I always say kind of well behaved. Okay. Okay. So laminar flow generally is orderly fluid flow where the fluid particles generally, the fluid particles in laminar flow are going to follow fixed, smooth paths. All right, so most of the time, you know, when you're talking about fluid mechanics, and probably the majority of your guys' fluid mechanics class has talked about laminar flow, okay? And so laminar flow, you know, usually looks something like this, right? We have kind of nice smooth lines where the flow, you know, the flow can change direction, that's fine. But, you know, usually it does so in kind of a slow, smooth kind of way, right? And so the reason laminar flow gets its name is that if you look at kind of a typical flow field like this, right, you'll see that the fluid kind of forms multiple different layers, or lamina, right? So, you know, that's kind of where it gets the name, because, you know, the laminar flow, you have these kind of nice, smooth, orderly layers of fluid flow, each with maybe a different velocity. Okay. Turbulent flow, on the other hand, is kind of the opposite. So turbulent flow is defined often as chaotic fluid flow, where the fluid particles, you know, maybe in the bulk, they may follow a path or fixed direction, but there's going to be a lot of random movements kind of in between. Okay. So turbulent flow, you know, it's a little bit hard to draw. You know, maybe look something like this. Okay. Okay. And so if you look at these paths, eventually the fluid flow makes it from left to right, but there's a lot of kind of chaos kind of in between there. Okay. Right. So why am I bringing this up? So, because essentially this is a heat transfer class. It's not a fluid mechanics class. So whether a flow is laminar or turbulent is going to affect how much convection heat transfer is going to occur. Right. And then, there's a lot of explanation that kind of leads up to this point, but I'll just kind of give you the conclusion first. Basically, when you have turbulence, when you compare turbulent flow to laminar flow, generally turbulence is going to enhance convection heat transfer. So you're going to have more heat loss or more heat transfer during turbulence rather than laminar flow. Okay. So laminar and turbulence is interesting because I think generally the intuition is that the faster your fluid flow is, the more likely turbulence is to occur, and there's a lot of truth to that. So, so fluid velocity or fluid speed is a big factor that determines turbulence. But there are actually ways to get turbulent flow even if you don't have very fast moving flow at all. And so we're going to go over different methods of doing that. And actually, for some situations, there are some situations where, maybe if you want to enhance convection heat transfer, one strategy is to actually purposely trip or purposely kind of induce turbulence in the flow to enhance that convection coefficient, right? And we've already actually seen applications where this might be valid. So if you're designing a fin to offload heat from like an engine or something like that, maybe you have some kind of tripwire, or maybe you have some kind of fluid mixer that induces turbulence, and that's going to enhance the thermal performance of your system. Okay. Any questions on this so far? Laminar turbulent flow? Okay, good. All right. So how do we determine if a flow is laminar or turbulent? Usually what we do is we compute what's called the Reynolds number. So have you guys seen the Reynolds number before in your fluid mechanics class? Good. Okay. So Reynolds number, it's a dimensionless number, so it doesn't have any dimensions to it. Okay. Very similar to the Biot number, but Reynolds number is almost used exclusively for fluid mechanics. And so there's two different forms depending on the parameters that you have. But probably the most common form that I use looks like this. Where U infinity here, this is the fluid velocity, usually the free stream velocity. So that's kind of important to remember. So, when you're plugging in a velocity for the Reynolds number, usually you don't plug in a number from the boundary layer. Usually you plug in the free stream or an average velocity. Okay. L here is some characteristic length of your geometry. Okay. So, we've already kind of seen this in the BO number. There's usually some characteristic length for your geometry. If not, you can compute it. You take the ratio of the volume over the surface area. Okay. And nu, if I could draw it properly. Nu here is the viscosity of the flow, which in this case, it's the kinematic viscosity. Okay. So I usually like this form of the Reynolds number just because there's only 3 terms. Another form of the Reynolds number that you may have seen utilizes the dynamic viscosity. So that one looks like the following. So we have U infinity times L times the density, rho, all divided by mu here. Okay. So mu here, this is dynamic viscosity. Okay. And rho here, this is the fluid density. Okay. Okay. So second form, that I think that's probably the first one that I've learned. And so that one, these 2 forms are exactly equivalent. Because if you take the dynamic viscosity, you divide it by the density, you get kinematic viscosity. It just depends on kind of which form is more convenient based on the parameters that you have. Okay. I think if you're looking up these properties in a table, I think for a gas, typically you're going to use the second form because gases usually give you the density and dynamic viscosity. But for liquids, what I've seen is that usually the viscosity is reported as kinematic viscosity. Okay, but they're both the same. And so whichever parameters you're given, you can use either form to compute the Reynolds number. Okay. So the Reynolds number, typically what we say is that there's usually some kind of threshold. So there's usually some critical Reynolds number for the flow geometry that you're looking at. Okay. So the critical Reynolds number, think of it as kind of like a threshold. So if you pass that threshold, so if your Reynolds number is greater than this, then you have turbulent flow. But if your Reynolds number is less than this critical, then you have laminar flow. And so that critical the value of that critical Reynolds number depends on the geometry. Okay. So we're going to go over a few different situations where the critical Reynolds number is going to be different. Okay. So for example, for external flow, right? So this is flow that's, not bounded or not constrained. The critical Reynolds number is 5 times 10 to the 5th. So if your Reynolds number exceeds that, like say you have a Reynolds number of 1 million, then you're going to have turbulent flow. Okay. All right. Any questions on this so far? Okay, good. All right. So the thing about turbulence too is that it's not like a switch that's flipped, right? And so it's not that your flow is laminar, and then once you get past this critical number, it all of a sudden it decides to be turbulent. There is some flow transition that occurs, in between these. And so, I know the way that it's usually described like this in fluid mechanics textbooks, but it's not like this. And so it's not like, you have a Reynolds number 4.99 times 10 to the fifth, right? It's not like this has nice orderly flow, right? And so there's nothing magical that happens here where, once you kind of reach Reynolds number equal to 5.01 times 10 to the fifth, right? It's not like all of a sudden the flow just starts going crazy from here, right? It's not that big of a change like that. So once you're kind of close to the Reynolds number, things start to transition into turbulence. But usually for a lot of flows, either occur in two regimes. There's flows that are much less, or has a Reynolds number much less than the critical one. So something that's less than 10 to the fifth. And there's also flows that have Reynolds number much greater than this threshold as well. Okay. So most of the time you're going to be in either one of those two regimes. So either you're going to be very, very turbulent or very, very not turbulent, right? But if you're close to the critical Reynolds number, it's not like a binary transition. It's not like a sudden thing. There's some transition that occurs in between. Okay. It's like the meme that I always see, the difference between someone that's 5'11" versus someone that's 6 foot, it's not, it's not that big. So once you're kind of close, they all kind of look the same. Okay. All right. And so to that, let's kind of illustrate to see how a turbulent boundary layer typically forms on a flat surface. Okay. So this is going to be relevant for kind of what we're going to discuss next week. So next week, we're going to talk about external convection. Okay. So in other words, convection on surfaces that are in, a fairly external environment. Okay. All right. So let's say that we have a flat plate here. We have flow that is coming across. Okay. So this flow has some velocity u infinity. Okay. All right. And so once we strike the flat surface here, we know that a boundary layer is going to start to form. All right. And so, last time we talked a lot about the boundary layer. The boundary layer is just this transition region between the conditions at the plate and the conditions at the free stream. Okay. And so boundary layer will always form like this, where, it starts with 0 thickness, and the boundary layer eventually will grow, as you go along the plate. Okay. All right. So initially, no matter what the external flow looks like, initially when the boundary layer first starts to form, the boundary layer actually is laminar.
So this initial region right here, sometimes it's really small, but there's always a portion of the boundary layer which always starts with laminar flow. Okay. Usually, there's ways to get a turbulent boundary layer right from the beginning, but if there's nothing impeding the flow, there's nothing kind of weird about it, there's always going to be a laminar region of the boundary layer. And so if you kind of draw the velocity streamlines here, right, and so they all look fairly orderly. So they're all kind of parallel. You have nice laminae that kind of forms here, right? We have nice kind of orderly flow. Okay. Although eventually, there comes a time where there's a place where the flow is going to start to transition. Okay? And so when the flow starts to transition, the boundary layer, it's not going to have a nice sheet. Okay. And so in this region, the flow will start to kind of, get a little oscillatory, get a little funky. So this right here is known as the transition region. And let me use a different color. Okay. Okay. So, physically what's happening here is that the boundary layer is kind of growing a little bit too big. And so, once the boundary layer gets a bit too big, it's hard to kind of maintain that kind of orderly kind of structure. Just because the transition region is just getting much bigger and the differences are getting much bigger. Okay. Eventually, you're going to reach a point, if this flow continues and the fluid velocity is high enough, the boundary layer will start to grow at a much higher rate. Okay. And so in this region here, you start to have much more chaotic flow. So this region right here, we know this as the turbulent portion of the boundary layer, or the turbulent region. All right, so that's how a typical boundary layer develops. And so, there's usually a region which, starts out as fairly laminar. There's then a transition region as the boundary layer grows. And then once you kind of reach that threshold, so, once kind of the local Reynolds number kind of exceeds that threshold, that's when the flow starts to really get really turbulent. Okay. And kind of one of the important keys here is that the turbulent boundary layer grows at a much higher rate than the laminar boundary. Which is going to be relevant when we bring this back to convection heat transfer. Okay. Okay. Any questions on this? Okay. All right. So the reason I'm kind of bringing the boundary layer back into this discussion is that we need to talk about how this is going to affect convection, right? So, we know already that turbulence is going to enhance convection heat transfer, right? And now that we kind of understand how a boundary layer forms and what the flow patterns look like, we can kind of start to explain why, turbulence will enhance convection heat transfer. Right? Okay, so inside the boundary layer, it's important for us to talk about the differences between what's happening in the laminar region versus the turbulent region. Okay. So the main difference that you're gonna see, right, at least from kind of a numerical kind of standpoint, is that when you look at the gradients, and so velocity gradients, temperature gradients, these are gonna be greater in the turbulent boundary layer compared to the laminar boundary. Okay, so let me kind of illustrate that for you. So on the left-hand side here, we're gonna have laminar. On the right-hand side here, we're gonna have turbulent. And so for the laminar boundary layer, it's gonna look something like this. So you have this kind of nice parabolic flow pattern. Okay. Eventually, at the edge of the boundary layer, the fluid velocity is going to reach U infinity. Okay. And then for the turbulent boundary layer, eventually the flow is going to reach up to U infinity again, right? Right. So that's no different. But the path that it takes to get there is very different. So if you look at the laminar boundary layer, we have this kind of very nice, smooth, steady transition. For a turbulent boundary layer, because you have so much chaotic flow, what's going to happen is that near the surface, you're gonna have a very sharp gradient, and so you have a very sharp increase. And then once you kind of get past that region, then it kind of shortens out a little bit from there. Okay. So the big difference in between these two graphs is that if you look at the near wall region, okay, near the wall, you have much sharper, much more extreme variations or differences in velocity that occurs. And so if you compare that to the near wall region in the laminar boundary layer, you can see that the change is much less, much less sharp. Okay. So same thing is going to happen for the temperature as well. Right. So if you draw out kind of the profiles for the temperature boundary layer, they're going to look very similar. So again, we're going to have the laminar case versus the turbulent case. Okay. So for the laminar case, it's going to look something like this, where, if we have kind of a fairly hot plate, right? So let's say that we have a hot surface temperature TS. Eventually, the boundary layer has to cool to a free stream temperature T infinity. Okay. Right. And so for a laminar boundary layer, this is going to be a fairly kind of smooth kind of change. Okay. So this graph is a little bit hard to interpret. So So basically what I'm showing you here is that, you know, within the boundary layer, the temperature is changing steadily. Okay. It changes steadily from the temperature at the surface. And it's going to change up until you reach the free stream temperature, T infinity. Okay. So that's why you have kind of a nice, kind of steady kind of path to the left, just like that. Okay. All right. Whereas if you look at the same situation with the turbulent boundary layer, so same surface temperature, same free stream temperature. Okay. So you have T infinity, and I'm going to come over here a little bit. TS. Okay. The starting and ending points are the same for the turbulent boundary layer. It's just that, you know, you're going to have a much more rapid change near the surface compared to before. Okay. And so if you plot this path, you know, it may look something like this. So again, you have much more rapid change near the surface. All right. And, you know, I know this class is focused on heat transfer, but, you know, actually a lot of what we learn in heat transfer can be appropriate for mass transfer as well, right? In fact, you know, when I learned this when I was in college, the class was actually a hybrid between heat transfer and mass transfer together, just because the theory for both is actually very similar. So you're going to see these you're going to see these trends in differences in concentration gradient as well. Right? So just a little bit of a trivia kind of on the side. All right, any questions on the temperature boundary layer here? Differences between laminar and turbulent? Okay. All right, so, you know, hopefully what these kind of figures here show you is that, you know, the gradient is much higher when you have turbulence. And so if you were to kind of quantify this, or in other words, if we summarize this, okay, if we take the gradient, and so let me take the temperature for now, okay, and we look at this in the laminar case versus the turbulent case. Okay. So in other words, we're looking at the derivative of the temperature field with respect to y. So we're seeing how quickly the temperature is changing as we go in the y direction. Right. So hopefully kind of what I've convinced you is that for the turbulent case, the gradient is much, much bigger, okay, at least in the near surface region. Outside of that near surface region, you know, the laminar is able to kind of maintain that gradient much, much greater. But, you know, the only thing that really matters for convection is that near surface region, okay? So for our purposes, for the purposes of convection, we can say that the gradient in a turbulent boundary layer is much greater than the gradient in a laminar boundary layer, okay? And so what this means, right? If you go back to kind of the first equation that we went through today, which says that H is at least partially dependent on the temperature gradient, right? Remember that equation that we kind of talked about at the beginning, which I said we're not actually going to use this equation, but it's useful to know the trends, right? If we know that dt dy is greater in the turbulent boundary layer than in laminar one, it then stands to reason that your convection coefficient in a turbulent case is going to be greater than the convection coefficient in a laminar case. In other words, H laminar is less than H turbulent. Okay. Okay. So you'll see this kind of manifest itself over the next few weeks. And so next few weeks is going to be kind of, equation overload because we're going to be going over a lot of different equations. But you're going to see for every situation, there's going to be two separate equations. So there's going to be equation for a laminar version of this situation and a different formula for the turbulent version. Okay? So that's, a trend that you're going to see. And what you're going to see is that we're going to look at lots of different situations. So external flow over flat plate, external flow over a cylinder, internal flow with within a heat exchanger. So for every single one of these situations, every single situation is going to have two formulas, at least two formulas associated with them. Because you're going to have one for the laminar case and one for the turbulent case, right? It's a lot to keep track of, but I do actually have a handout for convection, which kind of summarizes kind of the whole unit, which it should be on Canvas already, but it may not. It may be in the files folder, not so much in the other folders. Okay. Okay. So that's kind of the fluid mechanics, kind of boundary layer explanation for why turbulence enhances heat transfer. There's a much simpler, much easier way to kind of describe it. So kind of an easier way to describe kind of why turbulence will enhance heat transfer has to do with the fact that turbulence has chaotic flow. And when you have chaotic flow is going to, enhance the amount of natural mixing that occurs within the fluid itself. And so, you can kind of observe this in your own life as well, right? So let's say that you just got a cup of house coffee from Starbucks and you want to add creamer to it, right? And so you pour the creamer in the coffee and you mix it with the little wooden stick that they give you, right? So if you mix the coffee, with the very kind of slow, kind of steady movements, it's going to take a while for that creamer to mix all the way through the coffee. But if you just, take your wooden stick and just like stir the hell out of it, right? Then that's going to enhance mixing a lot more greater, much more better, right? It's the same thing with cooking too. And so, if you're trying to mix an ingredient into a soup, usually you want to mix it fairly vigorously rather than, stirring it slowly. Although, the other thing you have to consider when cooking is you don't want to make a mess in your kitchen too. So you don't want to splash things, but if you want to mix things, well and thoroughly, you always use a very fast motion. You don't use a very slow motion, okay? So for heat transfer, it's the same thing. So when you have chaotic flow, a chaotic kind of random fluctuations, that's going to enhance mixing, and that includes heat and temperature as well. So that's kind of the, the Wikipedia definition for why turbulence enhances convection. But, now both ways. Now the fluid mechanics explanation with the boundary layers, but you also know kind of the one-liner way to explain it as well. Okay, any questions on turbulence here? Okay, so last thing I want to discuss before we head out for today, it's the last point in these notes as well, is non-dimensional numbers. Okay, so the thing about thermal fluids, and probably you've probably seen this already in this class, is that, people who work in this field, people who work in this area love their non-dimensional numbers. So, non-dimensional numbers are essentially numbers that don't have dimensions. And so they don't have any units associated with them. But usually the value of these numbers usually will tell you something important or some kind of feature of the system that you're trying to describe. So, we've already talked about one, which is the Reynolds number, right? Reynolds number is probably one of the most famous non-dimensional numbers out there, okay? Okay, so, you guys have no doubt used non-dimensional numbers in your previous classes before. But, I think a lesser point that's not often made is the reason these are non-dimensional is because oftentimes these non-dimensional numbers represent a ratio of some kind. So it's a ratio of some kind of behavior over another. Okay, so you're going to see me use this kind of methodology. You've actually already seen it used in the Biot number, okay? And so for the Reynolds number actually represents a ratio of the what are called the advective effects. So I should say fluid advection over the fluid viscosity. Actually, let me change this. So instead of advection, let me make it a bit more clear. We'll say fluid momentum. And that's a better way to put it. So most non-dimensional numbers that you see out there represent a ratio of some kind. So the Reynolds number kind of shows you a ratio of kind of the momentum forces within the fluid versus its viscosity forces. Okay? And that ratio, depending on the value of that ratio, will tell you something important about the flow. Okay. And so if we kind of, take what we've already learned about the Reynolds number for today, right? What this tells you is that a high value of Reynolds number will have much more fluid momentum relative to its fluid velocity. And if we kind of extrapolate this a bit further, right? Since we know that a high Reynolds number is going to lead to turbulent flow, right? What we can kind of extrapolate from this is that when your fluid momentum is high relative to the amount of viscosity that you have, that's what leads to turbulent flow. Okay. So, I think, we're going to be using non-dimensional numbers a lot in this unit, but I think it's always important to remember that the value of these non-dimensional numbers represent a ratio of some kind. Because, for any given complex engineering physical situation, there's almost always some degree of competing factors within the system, right? Momentum versus viscosity, thermal versus fluid, right? And so it's important to remember that all of these non-dimensional numbers represent a ratio of some kind, okay? And then you can use that to kind of tell you that this number is not just a number. This number tells you how high this effect is relative to this effect. Or if your non-dimensional number is low, that means your denominator might be higher than your numerator, okay? And so for the last 3 minutes that we have, I do want to introduce one more non-dimensional number. It's not the non-dimensional number. We'll go over that next time. But the one I want to go over today is called the Prandtl number. And of course, the annoying thing about these non-dimensional numbers is that they're all named after people. And so, if I just stop the class right now, you'll have no idea what the Prandtl number represents. Because, I don't think most people even know who Prandtl even was. I don't even know his first name. He's just Prandtl. Prandtl first name number. Okay. So the Prandtl number looks like the following. So it's nu over alpha here. Which, if we kind of apply our definition of non-dimensional numbers being ratios, this is exactly a ratio that we have here. And in fact, the ratio here on top is we have the kinematic viscosity. So we've seen that guy. We've seen that guy a lot today. Okay. Alpha, we've actually seen before in this class, but we haven't really talked about him all too much. Just because he's usually not that relevant for conduction. But alpha here is what's known as the thermal diffusivity. I can spell it right. So the thermal diffusivity kind of plays a similar role as the kinematic viscosity does for fluid momentum, okay? So what the Prandtl number here represents, this represents how easily, momentum can travel through a fluid versus heat. Right. So more viscous fluids, will transport momentum a lot more easily, right? Versus fluids that have a higher thermal diffusivity will allow for heat and temperature to diffuse a lot more easily as well. Okay. The main thing that this kind of affects is this number here tells you how quickly the boundary layer and the thermal boundary layer grow relative to each other. Because actually those two things can be different. And so, I think up to this point, we've kind of assumed that those two things are the same. But depending on the fluid, you can have different growth rates for the regular boundary layer and the thermal boundary. Okay. Okay. Any final questions on this before we wrap it up for today? Okay, all right, so next time I'll see you guys on Thursday will be for the midterm exam. I'll send an email today kind of reminding everyone what you can bring. And you know, what's, you know, will be provided and things like that. And then we'll pick this up again on Tuesday. And thank you guys for coming today. If you have last questions on the midterms, you know, definitely come up and ask. If not, I'll see you guys on Thursday. Yeah.
When we were talking about.
Yeah.
There was a symbol in the back. That, I don't know.
Oh, yeah, so that's, I usually use a tilde. So something like this. So all that means is that H is proportional to DT. Yeah. So they grow at the same rate. The higher DY is, the higher. Yeah, same rate. Proportional to. Tilde.
Tail.
Yeah.
Never heard of that.
Oh, thank
You're gonna use it. Thank you.
Yep.
Good question.
Yeah.
So, I know for the heat password or heat, passwords, it might be just easier if I show it.
Yeah.
But there's one part where it flips and they cancel out, but I'm kind of confused on where. Pull it sooner. Right here. I'm kind of confused on how you get that to be thinking. Some of the time,
This case, you're taking the integral, you flip this one. Taking the integral.
Oh.
So that's-
Oh, so I'm thinking the book.
You're taking the integral, you're taking the integral. So you're taking the integral. Because when you're taking the derivative, yeah. it's called-
Oh, okay, yeah,
Integral.
I get it all mixed up. Thank you.
Yeah.
Up to me.
Yes, I think I put it in there. I believe so. I think I have two in this one. What's the name again? Oh, yeah, I'm not sure. That's fine. Yeah, that's fine.
You know what? Thank you.
Yeah. Sure. Yeah. I got both. Yeah. Yeah, so for this one, so the shape factor is basically combine the effects of multi-dimensional. Because we have, you know, you look at the square channel, which you have a square channel, right? But you know, if you look at the pattern, this pattern here, this pattern.
If you want to study, I'm gonna
These are different. And so if you look at the heat that comes out here. That's why 2D reduction is
It's all good.
you have to look at two. With the shape factor kind of summarizes the heat transfer entire thing. To kind of one simple thing. Yeah, so it actually takes 3D and 2D back down to one.
Okay.
So the comparison there that I want to illustrate. The thermal resistance will do the same thing, take the difference in temperature, you divide by one. And so the shape.
Robinson used the thickness of the characteristic.
Yes.
That's LC.
Yeah.
Yeah, so we can do,
It is, yeah, sometimes it is, and so that's, I did that on purpose, so there's no ambiguity where you can use it.
Remember how to apply. I know we do have.
Yeah.
But what else? What is or something?
Yeah, so there's.
So you bought one, and then you just got the second over
It's basically like some kind of like. Okay, so we're gonna check for all three of these things. I think in this problem. I was general. Yeah. Yeah, so if you're given an H net. If there's thermal production here, you try to set the value. Yeah, so Q dot, so there is thermal production. I think the thing that's not here is there's no special.
Yeah.
So in that case.
Is that gonna be your main?
That's convection. Yep. That's like Q dot of thermal.
Okay, thank you.
Yep. What's up? What's up? Yep.
Yeah, I'm a.
Yep.
Temperature, right? So it's like. If we're solving for temperature.
So in the first part here, there's no T in the so you're basically just heating up the oven with the door closed, so there's no convection at all. Right, and so T of 0 in this case, or the initial condition, is that I think I set it to, well, maybe I didn't call it T infinity, but maybe it's the starting temperature of the oven.
Oh, so T in this case is gonna be the same as X's temperature, right? So they're
Exactly.
both 0.
Exactly.
Oh,
Yeah.
yeah, that makes sense.
Yeah.
So we assume that the initial temperature is 0.
Yes, usually the excess temperature is 0.
Yeah, usually, but inside the oven, we assume it's 0.
Exactly.